Hello and welcome to another past paper video where today we are doing the GCSE 2019 Physics Paper 1. And now question 1, light bulbs are labelled with a power input, and then for 1.1, what does the power input mean? And we're just given 4 options, with it being the charge transferred each second by the bulb, the current through the bulb, the energy transferred each second to the bulb, and the potential difference across the bulb. Now, the only one that's actually correct in this is the energy transferred each second to the bulb. If you think about it, the energy transferred each second by the bulb is the power output, the current is the current, and the potential difference is the difference. And then we're just asked to write the current that links current, potential difference, and power, and that is that power equals current times potential difference. When this paper was made, they didn't have formula sheets, or they had like limited formula sheets. Nowadays, you get all these formulas, but these questions still do occasionally appear. And then we're told a light bulb has a power input of 40 watts. The mains potential difference is 230 volts, and we're asked to calculate the current in the light bulb. So we just do power equals current times voltage. 40 equals 230 times I, which is the current. The current equals 230 over 40 equals 0.1739. which I rounded to 3 significant figures, as 3 significant figures is what they usually give it as. So the answer is 0.174 amps. Then we're shown some information about 3 different light bulbs. Light bulb P has a total power input of 6 watts, useful power output of 5.4 watts, and efficiency of 0.9, and then we're given some information for Q and R as well. And then we're asked to write down the equation which links efficiency, total power input, and useful power output. And we're told that efficiency equals useful power output over total power input. And once again, that's given in your formula booklets nowadays. And then we're asked to calculate the value of X in table 1. And we just rearrange the formula. So the efficiency is 0.3, the useful power output is X, and the total power input is 9, so it's 0.3 equals X over 9. Rearranging, you get X equals 2.7 watts. The most important mathematical skill you can have for GCSE physics is rearranging equations. Like, for example, we could have just left it in terms and then rearranged for useful power output, or just solving equations if you want to plug the numbers in first. You can do it either ways. You can rearrange the equation first, then plug the numbers in, but I personally prefer plugging the numbers in, then rearranging, because then it often simplifies easier. There are a couple cases where you want to do it in terms first. For example, when you're comparing kinetic energy to gravitational potential energy, if you do it in terms first, you can cancel the mass and save yourself a bit of work. Then for 1.6, in addition to power input, light bulbs should also be labelled with the rate at which they emit visible light, and we're asked to suggest why. And that is because bulbs also transfer thermal energy, so the efficiency of the light bulb also needs to be considered. So let's say we have the worst light bulb ever. And it's not even a light bulb, it's just a brick that you transfer energy into. It could have and you call it a light bulb. You could have a massive power input. You could have a power input that's like millions of watts. Yet if it's not emitting any visible light, it's not a very good light bulb. So you need to actually take into account the rate at which it emits visible light. Although if you're pumping millions of watts into anything, it's probably going to glow, and it's probably going to kill anything nearby. And then you don't need a light bulb because you're dead. And then for question 2, a student investigated the insulating properties of newspapers. Figure 1 shows the apparatus the student used. It's just a digital thermometer, hot water, metal can layers, newspaper, and we're shown their results. And then we're asked to describe a method the student could have used to obtain the results shown in figure 2, and that's like this nice thing. This is a 6 marker. All 6 markers that aren't math 6 markers, except in one specimen paper, and like 30% of 4 markers are leveled questions in which the continuity of your answer and how much actually makes sense is based. So like there's indicative content marks, like you could get 6 indicative content marks, but if your answer doesn't really make sense, doesn't meet the leveled criteria, you could be limited to a 4. So for the method the student used to obtain results, they heat water in a kettle, then put hot water in the metal can, starting off with no layers of newspaper. And then you use a measuring cylinder to measure the volume of water. I suppose you'd actually do that first. And then you measure the initial temperature, then use a stopwatch to measure a time of 5 minutes, then take the final temperature with the digital thermometer, and then you calculate temperature decrease. Then you repeat increasing the number of layers of newspapers each time, making sure to always use the same initial temperature of hot water and the same volume of hot water. And that would get you these results, like temperature decrease after 5 minutes with 0 layers of newspapers, and then you increase the layers of newspapers, repeating calculating the temperature decrease after 5 minutes each time. Next on, question 2.2, the student could have used a data logger with a temperature probe instead of the digital thermometer. Figure 3 shows the readings on the digital thermometer and data logger, and they're both 67.5. The data logger reports 10 readings every second. The student considered using a temperature probe and data logger. Explain why it was not necessary. Well, the digital thermometer and the data logger have the same resolution, 1 decimal place, so you don't get more precise readings using one or the other. And we only need to measure the start and end temperature, so we only need 2 readings 5 minutes apart. So having 10 readings every second doesn't help. And if you ever do computer science, it's sort of like having something run in the background. It's just unnecessary. It's unnecessary to have all these additional readings. For this particular experiment, there are experiments where a data logger and probe will be better. And then a scientist investigated how the maximum muscle power of humans varies with age and gender. The scientist asked volunteers to stand on a platform and to jump as high as they could. Figure 4 shows a volunteer taking part in the experiment and seemingly having quite a bit of fun. Although, if you do GCSE PE, you'll know you're like not meant to move like your arms when doing this experiment, or like you're not meant to like move your arms to like gain additional leverage. It's just meant to be like a straight jump. This is me complaining about AQA, the silly little drawing because it's inaccurate, but that doesn't actually affect the question. Electronic timer measured the time that the volunteer was in the air. The muscle power in watts per kilogram is calculated using the following equation. Muscle power equals 9.8 times jump height over time. One volunteer has a muscle power of 41 watts per kilogram. He was in the air for 0.12 seconds. Calculate his jump height. Well, it's 41 equals 9.8 times jump height over 0.12, just plugging the numbers in. Multiply both sides by 0.12. Divide both sides by 9.8 and you get a jump height of 0.502 meters. And then we're asked to write down the equation which links kinetic energy, mass and speed, and that is kinetic energy equals 0.5 times mass times speed squared. And then we're told one volunteer had a kinetic energy of 270 joules and a speed of 3 meters per second at the moment he left the ground. We're asked to calculate his mass. Once again, it's just plugging the numbers in. 270 equals 0.5 times mass times 3 squared, which is 9. And then you just rearrange, multiply by 2, divide by 9, and you get a mass equals 60. Like, just think about how many questions so far have just been rearranging equations. If you know how to rearrange equations, physics is easy. And then for figure 5 shows the scientist results. Muscle power in watts per kilogram and the age of volunteers, and then a non-dotted line for men and a dotted line for females. And then we're asked to compare the muscle power of males with the power of females. This is a level answer, but there's so many different things you could talk about. I've just included all of them. If you want to pause and read these, would be a good use of your time, talking about like all the different things you could analyze from this data, like females being higher earlier on, men being higher for a prolonged period of time, women having a slightly earlier drop-off, men having a lot later drop-off, them slowly coming together at the end. But the important things are, you need to ignore comments to strength. Once again, a GCSE PE thing, strength and power. strength and muscle power aren't the same thing, because like strength is like power is relevant to time, but also you have to stay focused to what you're talking about. It's asking you to compare the muscle power, not the strength. So it's important not to use synonyms where it doesn't use synonyms. So much indicative content for a 4 marker. I've used bullet points just to show you all the indicative content. Don't actually use bullet points. This is just to show you all the things you could include in a well-structured answer. And then for 3.5, the muscle power of each volunteer was measured 5 times. The highest muscle power reading was recorded instead of calculating an average, and were asked to suggest one reason why. And that's because maximum muscle power was being investigated, not average muscle power. If you go all the way back, investigated how the maximum muscle power. So that shows like how important the continuity of the question is. How you need to like read this like beginning blurb bit, and then something from the beginning blurb bit comes up at the very end of that question. Then we're told electric cars have motors that are powered by a battery. Diesel cars have engines that are powered by diesel fuel. Table 2 compares one type of electric car with one type of diesel car. And then we're just given energy density for both, mass of power source, total mass, and time to recharge battery or refuel tank in minutes. And we're told that the electric car has a range of 400 kilometers and the diesel car has a range of 1,120 kilometers. Explain the difference in the time needed to complete a 500-kilometer journey using the electric car compared with the diesel car. And we're told to assume both cars travel at the same speed. The electric car's journey will take a longer time as it will need to stop for 40 minutes to recharge. And that's because the 400-meter range is less than the 500 meters it will travel. And then we're told energy density is the amount of energy stored per kilogram of the energy source. So we're given both the energy density and the mass. Show why the diesel car has a greater range than the electric car. And that's because you simply multiply the energy density in megajoules per kilogram times the mass of the power source in kilograms, and then you get the overall total energy stored in each power source. And for diesel, that is 2,295 megajoules, and for the battery, it's 266 megajoules. So the diesel stores more energy than the battery, and so the diesel car has a higher range. We're also told to assume the efficiency of the two cars is the same, which won't actually be true, but we're meant to assume that the same proportion of both of these energies goes towards actually driving the car. Engineers have developed a way of charging electric cars while they are driving along the road. Coils of wire buried underneath the road transfer energy to the car's battery as the car is passing over the coils, and then figure 6 shows a charging lane on a motorway. These aren't real yet. So there's 2 advantages of using this method to charge electrical cars compared with plugging them into the mains electricity supplies. Cars do not need to stop to recharge, so that would fix the range issue the cars were having, and a smaller battery is needed in the car. Like, you won't need to have a really big battery to allow it to go on forever if it's charging itself while on the motorway. It's like how you can get away with having a phone with a bad battery if you're always carrying around a power bank. Okay, that's not really that good an analogy, but there's like 20 other reasons on the mark scheme being like you don't have to find an electrical charging station, because when this was made in 2019, electrical charging stations were less popular, and just multiple other things. It encourages people to have eco-friendly cars and all that stuff. So many reasons on the mark scheme. And then 4.4, when electrical cars are not being driven, energy stored in their batteries could be used to meet sudden peaks in electricity demand, and we're asked to suggest how. And that is that fact that when cars are plugged in, the energy from the car batteries could be transferred back to the national grid. So you could use the electric cars as like temporary batteries, and then if there's a sudden spike of electricity, you use the electricity from the cars that are plugged in on people's driveways and stuff to help meet the demand. And then for question 5, Polonium-210, which is we're just given a symbol for, is a radioactive isotope that decays by emitting alpha radiation, and we're asked to complete the decay equation for polonium-210, and we just need to balance it out. So 206 plus 4 equals 210, 82 plus 2 equals 84, and then we're asked to explain why the contamination of the inside of the human body by a radioactive material that emits alpha radiation is highly dangerous. And that's the fact that alpha radiation is highly ionizing, causing an increased risk of cancer, radiation sickness, organ failure, mutation of genes, and damage of cells until the radioactive material is removed. And this is different to gamma radiation. If you ate gamma radiation isn't that highly ionizing, and it passes through stuff, so the gamma radiation would be able to pass out of your body. In fact, that's used in some medicine by placing a tracer that emits gamma radiation so you can track where it is in the body. But with alpha radiation, it can't pass through the body. It's really highly ionizing, so it just keeps hurting you and damaging your cells. In fact, there are a few cases of espionage where people's food has been poisoned with alpha radiation, or a radioactive material that emits alpha radiation. And then for 5.3, a sample of polonium-210 was left for 414 days. After this time, it had a mass of 1.45 times 10 to the minus 4 grams. The half-life of polonium-210 is 138 days, and we're asked to calculate the initial mass of the sample. Well, firstly, we have to work out how many half-lives 414 days is, and if you divide 414 by 138, you work out it's 3 half-lives. And then you simply divide it, because it gets halved 3 times. It gets divided by 2 cubed, which is 8. So you divide 1.45 times 10 to the minus 4 by 8 to get 1.16 times 10 to the power of minus 3, which is 0.00116 grams. Then for question 6, figure 7 shows the person using an electric lawnmower. The lawnmower is connected to the mains electricity supply. What is the frequency of the mains electricity supply in the UK? It's 50 hertz, and you just have to remember this. This is something you just have to remember. You just have to remember the unit. You have to remember the number. Just like how you'd have to remember the mains voltage and unit for that, and that is 230 volts. But thankfully they gave it earlier in the paper, so that's not necessary. The lawnmower has a switch on each side of the handle. Figure 8 shows the circuit diagram for the lawnmower. The motor in the lawnmower can only be turned on when the person using it holds the handle of the lawnmower with both hands. Explain why. Originally, this sort of looks like a safety question. Why would you want it to only be able to be turned on with both hands? But it's not actually a safety question. It just wants you to explain that both switches need to be closed to complete the series circuit and allow charge to flow. Then the power input to the motor is 1.8 kilowatts. The resistance of the motor is 32 ohms. Calculate the current in the motor, and this is the formula you're given on your formula sheet. P equals I squared times R. Plug the numbers in. I squared equals 56.25. You have a calculator, so it's always very easy to actually rearrange the numbers as long as you don't put stuff into your calculator wrong, and you get I equals 7.5 amps. Then the useful power output from the motor is 1.5 kilowatts. Calculate the time it takes for the motor to transfer 450,000 joules of useful energy. And we simply use another formula from the formula book, power equals energy over time. Plug that in, rearrange it by multiplying by time, dividing by 1,500. Time equals 450,000 divided by 1,500. and that equals 300 seconds or 5 minutes, but it asks for it in seconds. Then moving on to question 7. Figure 9 shows a person sliding down a zip wire. As the person slides down a zip wire, the change in gravitational potential energy of the person is 1.47 kilojoules. The mass of the person is 60 kilograms, and gravitational field strength equals 9.8 newtons per kilogram, and we're asked to calculate the change in vertical height of the person, and the formula is E, once again in the formula book, E equals mgh, where it's specifically delta h, or change in height. One thing I haven't brought up yet is I've just been, it's second nature to me at this point to just convert kilojoules to joules by multiplying by 1,000, but I know certain people struggle with unit prefixes or just forget to do it. So if you want to see a video on unit prefixes and my acronym, Terry's gun malfunctioned, killing multiple mews, then let me know. But until then, I'm just going to assume you know how to multiply it by 1,000. So you get 1,470 equals 60 times 9.8 times height, divide by 60 times 9.8, and you get a height of 2.5 meters. Then for 7.2, as the person moves down the zip line, her increase in kinetic energy is less than her decrease in gravitational potential energy, and we're asked to explain why. If it was a closed system, then the increase in kinetic energy would be exactly equal to the gravitational potential energy. And there's questions in other papers where we have to assume it's a closed system and do maths with that. But we're told here that it's less than, and we're asked to explain why. And that's due to thermal energy is lost to the surroundings due to work done against air resistance or like friction against the wire. In real life, the only truly closed system is the universe, to a certain extent. I'm sure there's quantum physicists who know better than me. I'm doing a maths degree. Quantum physics is not really my area of expertise. But in certain GCSE physics problems, we assume things are closed systems to allow us to do the maths, although it will never be 100% accurate to real life. And then for 7.3, different people have different speeds at the end of the zip wire. Explain why. Different people have different surface areas, so would be affected by air resistance differently. And you can't talk about the mass affecting kinetic or gravitational energy. That is because kinetic energy equals 1 over 2 mv squared, and gravitational potential energy equals mgh. So if you're converting gravitational potential energy to kinetic energy, the masses cancel out. And they've had some really good questions about this. The mass doesn't affect the speed. Of course, it affects the speed in some sort of way because of terminal velocity and stuff like that. But it doesn't affect the transfer of gravitational energy to kinetic energy. That's why everything accelerates downwards at 9.8 meters per second squared. Then moving on to question 8. A student investigated the thermal conductivity of different metals, and we're just given the method. Measure the mass of an ice cube, put the ice cube on a metal block which is at room temperature. Measure the mass of the ice cube after 1 minute, repeat with other blocks of the same mass made from different metals. And then we're just showing the results for the different metals, initial mass of ice cube, final mass of ice cube, and the change in temperature. And we're asked, why is it important that the initial temperature of each column was the same, of each ice cube was the same? And that's because initial temperature is a control variable. And as a quick recap, control variables are what you keep the same. Independent variable is what you change, and the dependent variable is what you measure. And then we're asked which metal had the highest thermal conductivity, and we're asked to give a reason for the answer. The answer is it's copper, and that's because it has the greatest change in mass. And you can see that it has the greatest change in mass, and that's because the copper absorbs heat the quickest, causing it to melt, and causing the ice cube to shrink the most because it has the best thermal conductivity. And then we're asked to suggest one source of random error in the student's investigation, and that is that the variation in initial mass of the ice cube. So you can see that the ice cubes all have slightly different initial masses. And if you think about it, if you have a very massive cube of ice, obviously it's going to melt, it's going to lose more mass. This is an extreme example, but if you have a ice cube that weighs a kilogram, it's going to lose a lot of mass. However, if you have an ice cube that weighs 1 gram, it can technically only lose a gram of mass. Should probably stop doing analogies, they're not very good. And then for 8.4, an ice cube has a temperature of minus 15 degrees Celsius. The total thermal energy needed to raise the temperature of this ice cube to 0 degrees Celsius and completely melt the ice cube is 5,848 joules. The specific heat capacity of ice is 2,100 joules per kilogram times joules per kilogram per degree Celsius. And then the specific latent heat of fusion of ice is 334,000 joules per kilogram, and we're asked to calculate the mass of the ice cube. Well, two formulas from the formula sheet. The energy needed to change the temperature is energy equals mass times the specific heat capacity times change in temperature. The actual symbol for change in temperature is delta theta. I'm just doing T because my keyboard doesn't have delta theta. And the energy to change state equals mass times the latent heat of fusion. Well, because you need to both raise the temperature and change state, you add both of those together and then just plug the numbers in. Specific heat capacity is 2100, change in temperature is 15, the mass, and then the specific latent heat of fusion is that. Do a bit of algebra, add in, combine in the like terms of m, and then just divide by 365,500 to get 0.016 kilograms. And then for question 9, a student measured the width of a solid metal cube using a digital micrometer. Figure 11 shows the micrometer. The resolution of the micrometer is 0.01 millimeters. The student could have used a meter rule to affect the width of the cube. Explain how a meter rule would have affected the accuracy of the student's measurement of width. A meter rule has a lower resolution, so is less accurate than the micrometer screw gauge. Fun fact, a rule is different to a ruler. The ruler has those little bits at the end which aren't actually used to measure anything, while a rule doesn't have those bits at the end. That does not matter for GCSE in the slightest. If you get it wrong, they'll still give you the mark. But I did lose marks at A level for doing that a couple years ago. And then 9.2, the mass of the metal cube was measured using a top pan balance. The balance had a zero error. Explain how the zero error may be corrected after readings had been taken from the balance. Well, we recorded the value of the zero error when there is no object in the balance, and then you just subtract or add the value of the zero error. So for example, if there's nothing on there and it says the weight is minus a gram, you just add a gram to all your results. And if it says the weight is a gram, when there's nothing on there, you minus a gram from all your results. And then for 9.3, the width of the cube was 18.45 millimeters and the density of the cube was 8 times 10 to the 3 kilogram per meter cubed. And then we're asked to calculate the mass of the cube. Now you could convert it to meters, you could do it in millimeters cubed, then convert it to meters cubed at the end, but then you'd have to divide by 1,000 cubed because of how scale factors work in terms of area and volume. I have a really good video on that because I saw some mathematically incorrect graffiti where I live, and the graffiti said 2,000 meters cubed is the same as 2 kilometers cubed. And this is why you stay in school, kids, so your graffiti can be mathematically accurate so you don't piss me off and end up on YouTube. Anyways, I need to cut out me swearing, great. V, and then so you convert millimeters cubed into meters, and then you just cubed it in terms of meters to end up with 6.28 times 10 to the power of minus 6 meters cubed. And then you simply use the formula density equals mass over volume, rearrange it for mass. I don't know why I rearranged first instead of put numbers in. Mass equals density times volume, and you just put all of that into your calculator and you get a final answer of 0.0502 kilograms. Then for question 10, figure 12 shows a student after rubbing a balloon on his hair. The balloon and the hair have become charged. Describe the force that acts on the student's hair in figure 12. Now, the non-contact electrostatic force of attraction between hair and balloon. So that's the type of force it is. There's nothing touching, so it's a non-contact force, and they're going towards each other, so they're a force of attraction. And I just included the word electrostatic because that's technically what force it is. It isn't necessary. Should it be necessary? Probably. Am I going to complain about AQA? I have enough videos doing that. Then moving on to 10.2, an earth conductor was brought near the charged student. A spark jumped between the conductor and the student. The potential difference between the conductor and the student was 2.5 kilovolts. The energy transferred by the student was 0.005 joules. And we're asked to calculate the energy transferred by the spark. Once again, on the formula sheet, energy equals charge times voltage, 0.005 divided by 2,500 equals the charge. So the charge is 2 times 10 to the power of minus 6. Doesn't ask for it in standard form, so I gave the answer in standard form here, then just did a bunch of zeros because I felt like it. And then for 10.3, a defibrillator can transfer a charge to regulate a person's heartbeat, and we're shown a defibrillator. When a defibrillator is in use, a potential difference of 4,800 volts is applied across the person's chest. A charge of 0.16 coulombs passes through the person's chest in 4 milliseconds, and we're asked to calculate the resistance of the person's chest. And we're just given that charge equals current times time, because current is the rate of flow of charge. 0.16 equals I, the current, times 0.004, because you're converting milliseconds into seconds. Doing some rearranging, you get the current equals 40 amps. And then you use another formula from the formula booklet, V equals IR, to just 4,800 equals 40 times R equals 120. So we get the resistance of 120 ohms. Now you may be wondering, because you're using multiple formulas from the formula booklet, how do you know what formula to use? Basically, you write out all the different units you have, and then you look for a formula that you have all the units for besides one. And then you sort of repeat that process, because you didn't have amps, but you had charge and time. So you look at the charge, current, time formula, get current, look for a formula which has current and resistance, and you just keep repeating that process until you can work out your answer. And then for question 11, figure 14 shows a Bunsen burner heating some water in a beaker. Eventually the water changes into steam. Explain how the internal energy of the water changes as it is heated from 20 degrees to 25 degrees Celsius. And the mean kinetic energy of the particles increases, which increases the internal temperature. And we're asked how the particle model of gas is used to explain the difference in density between a liquid and a gas. And that is, particles in a gas have more potential energy than particles in a liquid. Temperature dictates the amount of kinetic energy in particles. State indicates the amount of potential energy in particles. Once again, that's something which you just need to know for GCSE, but you'll get to truly understand it if you do A-level. And then for 11.3, a student measured the mass of boiling water that was turned into steam in 5 minutes. Explain how the student could have used this information to estimate the power output of the Bunsen burner in watts. And that's because the energy given to the water equals mass times the latent heat of fusion. Actually, I think because it's boiling, it's latent heat of vaporization. And then energy equals power times time. So you sub that in to get power times time equals mass times latent heat of fusion. and then you get power equals mass times latent heat of fusion over time, where t is in seconds, or like 300 seconds. So if you have the mass, the latent heat of fusion, and the time it takes to boil, you can work out an estimate for the power output. Anyway, that's the end of that video. If you've enjoyed it, make sure to like and subscribe for more past paper videos. I'm pivoting from doing my... Hello everybody, I'm explaining a different GCSE maths question every day. I'm pivoting from that to doing past paper videos, because as much as I enjoy doing a random GCSE maths question every day, this is more sustainable and more helpful to people. So I'm pivoting to these. GCSE, that series will return. Probably not for year 11s. It probably will return in September-ish, where I have time over summer to get a large amount of them, because I was only able to do like a few a day and I was getting behind with everything like uni work and actual work. Yeah. So if you've enjoyed that video, make sure to like and subscribe, and I'll see you next time. If OBS didn't work, I'm going to kill myself.